Okay, so let's unpack this. There's this fundamental human skill, right?
Yeah.
Reasoning about what other people are going to do, what they're thinking.
Mm-hmm.
It's an intuition we use, I mean, hundreds of times a day, probably without even noticing. And there is no better example of this than driving through a busy intersection.
That is the perfect social engineering task, isn't it? When you get to a complex situation, like, say,
No.
you need to make an unprotected left turn against traffic.
Right.
Your decision isn't just about, speed and braking distance and physics.
Yeah.
It's fundamentally about psychology. It's a negotiation.
Absolutely. You don't have the right of way, but you have to get across. So you signal, you kind of size up the other car, maybe you edge forward a little bit,
And that other driver might yield to you.
or they might not.
Exactly. And a competent human driver is constantly doing this contingency planning. They don't have one single fixed plan of action.
No.
Their mind is running this conditional decision tree. It's if I signal, they might slow down. So plan A is they yield, I go. But, and this is the crucial part, I need a plan B.
Right, the backup plan.
Plan B, they don't yield, I stop immediately, and I have enough space to do it safely. These are all conditional actions based on a really uncertain outcome.
And that second-by-second internal negotiation, that is the entire problem for AI right now.
It is.
Most autonomous systems, they sort of decouple these two critical things. Prediction, so how others will act, and planning, which is what I should do. And that just fails completely when two agents are so dependent on each other.
It creates this fundamental gap in their ability to operate in the real world. Because the AI can't model how its own actions, like edging forward, might cause a human to brake, it just assumes the worst-case scenario. All the time.
And that failure mode has the perfect name. The frozen robot problem.
It's so good.
Yeah, when it's faced with uncertainty it can't actively resolve, the robot just becomes, well, underconfident and totally passive. Instead of acting and negotiating, it just waits forever.
It becomes paralyzed.
We've all seen those videos, right?
Yeah.
Autonomous cars stuck at a four-way stop or they're too cautious to merge. That's the frozen robot.
And what's so fascinating is that the robot's single-minded focus on safety, through these fixed conservative plans, it results in complete inefficiency. It solves the safety problem by just avoiding interaction altogether, which makes it unusable.
So our mission today is to dive deep into a new approach that's designed specifically to fix this trade-off between being safe and being efficient. It's called Contingencies from Observations, or CFO. And we're looking at sources that describe how this system learns that very human-like anticipatory skill end to end.
Right. So this approach, it transforms those rigid fixed action sequences, what we'd call open-loop control, into these adaptive conditional policies, closed-loop systems that can actually react to what they're seeing in real time. That's the key to making an autonomous system that's not just safe, but also, socially competent.
The core goal of this deep dive, then, is to show you how CFO fundamentally changes the AI's relationship with its environment. It takes it out of that frozen state and lets it be both safe and efficient by modeling this mutual influence and generating these robust conditional decision trees. So let's start at the beginning, because the structural difference between the old way and this new way is just, it's so critical. What is the fundamental difference between a non-contingent trajectory and a contingent policy?
Okay, so standard, traditional planning methods, especially stuff from robotics like model predictive control or MPC, they output a very simple sequence of future actions. We call this a fixed trajectory.
A fixed path.
Exactly. And mathematically, that plan is only a function of time. It just says, at t equals 1, do x. At t equals 2, do y. At t equals 3, do z.
And that plan, once it's launched, it's followed blindly, right?
Blindly. It is, by definition, non-contingent. The robot's actions are fixed no matter what happens in the world after that plan is launched.
So if a pedestrian steps out at second 3,
your plan is still accelerate, turn, brake, which is, of course, a catastrophe.
The GPS analogy we used earlier really nails this. Non-contingent planning is like following GPS directions blindly into a traffic jam.
Right. It assumes the future is static, but CFO, it outputs a policy.
And a policy is different how?
A policy is not a sequence of actions, it's a function. It's a function of future time steps and future observations. It's a whole decision tree, like a blueprint for how to react.
So it's not just planning what to do, it's planning what to do if.
Precisely. It says, at second 3, if my sensors see a pedestrian, then I execute the emergency brake plan. If the path is clear, then I continue accelerating. It's contingent on what it actually observes.
So the robot isn't just reacting, it's planning its reactions ahead of
Hmm.
time. It's pre-calculating all those branching paths.
Yes, and this brings us to the core deficiency that causes the frozen robot problem. These open-loop non-contingent plans, they ignore mutual influence. And this failure comes from ignoring two crucial facts about any social task like driving.
Okay, lay out those two facts
Yeah,
for
yeah,
us
yeah.
because I think understanding the failure here is the key to seeing why the solution is so smart.
Fact 1. Standard planners ignore how other agents will react to the robot's actions. They treat the human driver as this totally independent actor whose behavior is fixed.
So it assumes if the robot moves, the human's path won't change at all.
Not at all. And fact 2 is that they ignore how the robot's own future actions should change based on what those other agents do.
Ah,
So even if the human does react, say they slam on their brakes, the robot's fixed plan doesn't have a safe, efficient, pre-planned way to recover. It's still just focused on its own original path.
and that second point, the inability to change its plan based on interaction, that's where the frozen robot comes from.
That's it.
If its plan is fixed to just wait outside the intersection, it never even tries the action that might encourage cooperation, like edging forward. It misses the chance to negotiate.
It defaults to this super pessimistic assumption. Because it can't guarantee a safe path on a fixed trajectory, it just chooses the path of doing nothing, maximum immobility.
So it's safe, sure, but only because it's not actually participating in traffic.
It's taken itself out of the game.
To really get this, the source material gives us this great conceptual framework, using these probabilistic graphical models to show 4 different ways planners can model interaction. So let's walk through the 3 broken ones first.
Okay. The first and the most common is robot leader planning. This is your standard MPC. The key thing here is that the planner only models the robot's deterministic actions. The robot's future is not contingent on the human's future.
Which means its action trajectory is totally independent of what the human does next. Underconfident, passive, slow.
Exactly. It's the literal definition of the frozen robot state. It can't influence, it can't react effectively.
Okay, so what's the next model?
The next one is a little better. It's often called human leader planning or passively contingent planning. So here the robot does plan contingent actions. It can react to the human.
There's a but.
The model assumes the human is the leader and that the human's behavior is independent of the robot's future actions.
Ah, I see the subtlety there. So the robot can react to something the human has already done, but it can't plan a move, like signaling, expecting that move to cause the human to yield later.
Correct. The human's path is sort of treated as fixed, and the robot just follows. It can observe, it can follow, but it can't negotiate. It can't provoke a favorable response, so it's still underconfident.
Okay, now for the third failure mode, which sounds like the complete opposite of the frozen robot. Joint planning. This is the arrogant planner.
This is where the model gets a little full of itself. It assumes the robot can control all the agents in the scene, both itself and the human. It plans one single, globally optimal joint trajectory for everyone.
It sounds like it's driving like a New York City cabbie, just assuming everyone else will get out of its way because it knows the best path.
That is the perfect analogy. The source calls this overconfident behavior. If the planner assumes the human will yield because that's the fastest outcome for everyone, and it plans an aggressive turn based on that,
The moment the human doesn't do that.
the robot is already committed to a dangerous path with no way out. It's fundamentally unsafe.
So we have the frozen robot, who's too safe and slow,
Mm.
the passive follower, who can react but not lead, and the aggressive driver, who's fast but crashes.
Right.
And that leaves us with the model we're aiming for, the one that inspires CFO, co-leader planning.
The co-leader approach is the sweet spot. It's the optimal, actively contingent framework. It plans a policy that's designed to both influence and be influenced by the, stochastic, probabilistic behavior of the human. It sees the robot as an active participant.
So it captures the full feedback loop. My action now impacts their decision next, and my action after that is contingent on what I see them do.
Exactly. This is what allows the robot to plan to probe or to negotiate. And crucially, CFO does this by using a learned behavioral model from real-world data instead of using brittle, hand-coded rules, which is what a lot of older attempts at this did. That data-driven approach is what makes it work.
Okay, so let's take all that theory and apply it to the critical test case, that unprotected left turn. This is the ultimate multi-agent scenario that needs negotiation. We can see it perfectly in Figure 1 from the source.
Yeah, this scenario is so challenging because the uncertainty is so high. Will they yield or not? The robot can't wait forever, but it can't just gamble and go. It has to actively gather information to resolve that uncertainty.
So let's focus on how the old way fails here. A non-contingent planner. Its best fixed trajectory has to be the safest one.
Yes. And because that fixed path has to be safe under all possibilities, the human yields, the human speeds up, the only truly safe fixed path is to assume the worst.
Which means what?
The plan is simply to wait. Wait outside the intersection until the other car has completely passed and the path is 100% clear.
So the non-contingent planner's sequence of decisions is just, wait, turn after human.
Correct. It completely misses the chance to negotiate. If that human driver was actually going to be nice and yield, the robot, locked into its waiting plan, never makes the move entering the intersection. That would have signaled its intent and gotten that cooperation.
It's a perfect illustration of the frozen robot problem causing this massive inefficiency.
Totally. But the CFO solution, the contingent planner, it comes up with a much better conditional result. It sees the intersection not as a barrier, but as a source of information. The optimal contingent plan includes an active move designed to resolve the uncertainty. The robot's first planned action is to safely enter the intersection, just enough to signal its intent and see how the human reacts.
And once it gets that reaction,
Its conditional plan kicks in. Wait and brake if the human doesn't yield, or accelerate and turn if the human does yield.
so it's a branching path. It's not A, then B, then C. It's A, then maybe B1 or maybe B2.
Exactly. And this gets us to the core idea of active contingency. It's not just about reacting to what the human does, it's about planning to provoke a clear response from them.
Okay, define that provocation mechanism. How does the robot actively seek out that information?
It uses standard, socially understood driving signals. We're modeling the human's future behavior as being contingent on our actions.
So we can influence them to get the information we need.
Right. And in driving, you have explicit signals and implicit ones. The explicit one is obvious, right?
Turn signal.
The turn signal indicator. It tells the other driver, I intend to occupy this space.
But the implicit signal is often the more powerful one in a negotiation.
For sure. The implicit signal is that subtle maneuver. Edging the car slightly into the intersection or slowing down a lot right before you enter. It forces the other driver to make a choice and show their hand.
They either brake and yield or they speed up to get through.
And just like that, the robot has used its own actions to resolve the uncertainty about the human's path.
And the crucial safety piece here is that the plan has to have a safe out if the human doesn't cooperate.
Always. The Collier model in practice means I act to negotiate, I observe the reaction, and I have a safe, pre-planned backup if the reaction is hostile. This is how it can be efficient by negotiating without ever sacrificing safety.
The complexity of these decision trees must be huge, though. A 10-second plan with just 2 choices per second. That's thousands of possible paths. This is where the technical innovation of CFO comes in, right? The planning space.
Yeah, that's the engineering challenge. How do you efficiently represent and optimize over all these forking paths in real time? You can't just search the entire physical space of all possible car positions. It's computationally impossible.
So CFO needs a more compact way to represent its plans. And this is where the autoregressive normalizing flow model comes in. Okay, let's break that down. It sounds dense, but it's key.
The core idea is instead of modeling the space of trajectories, we're going to model the space of policies. The flow model is like a transformation, a link between a simple searchable space, which we'll call Z, and the complex physical world, which we'll call X.
So what is the Z space exactly?
Z is a space of policy parameters. Think of Z as a set of knobs or controls that determine the shape of the robot's decision tree. And Z is a simple space, like a standard bell curve, which makes it really easy to search.
So instead of searching the huge, messy space of physical car movements, X, we're searching the much smaller, cleaner space of policy knobs, Z.
Precisely. And the flow model is the function that transforms a specific set of knobs Z into the resulting physical outcome X. And the genius of using a normalizing flow is that this transformation is invertible.
Why is invertibility so important?
It means that for every unique set of knobs Z, there is one unique physical outcome X, and vice versa. It guarantees that the space of plans is both compact and rich. It covers all the options you need without being redundant, and it lets us do complex probability math really efficiently, which we'll need for the optimization.
So we found a way to efficiently package up a complex branching policy. This lets us find the best plan, second best, and so on very quickly. It's how we can actually optimize those big decision trees needed for active contingency.
Ready.
Okay, so we've got the why, the need for contingency, and the how, the mathematical representation. Now let's get the engine. How is CFO actually built and deployed? Let's turn to the core architecture in Figure 3.
So the CFO system runs in this fast, continuous loop when it's deployed, making decisions many times a second. And it very elegantly separates the cognitive task of planning from the physical task of execution.
Okay, let's break down that loop. What kicks off the cycle?
The cycle starts with the input layer. The contingency planner gets three key things: the current high-dimensional sensory observations, the overall goal, and that crucial learned behavioral model.
And that sensory observation, it's not just a simple coordinate, is it?
No, absolutely not. It includes the car's current position, sure, but crucially, it gets high-dimensional info. The source specifies that it's a LiDAR range map image.
Which is huge.
It's huge. It grounds the planning in the visual spatial reality of the entire scene, curbs, obstacles, all the other agents.
Mm.
It lets the model scale to real complex environments, not just simple simulations.
So the planner sees the scene, it knows the goal, and it applies its knowledge of how things behave. What does it output?
It outputs a multi-step plan, which, remember, is a policy, not a fixed path. And then that policy is executed for just one step.
One step at a time.
Right. It gives you the target position for the very next moment, which is then handed off to a lower-level controller.
So that target position goes to a standard proportional, or P, controller.
Correct. And that controller handles the low-level stuff, translating that desired position into actual steering, throttle, and braking.
That separation is brilliant. The heavy lifting, the complex social reasoning, happens at the policy level. The simple job of physically moving the car is handled by a basic, proven controller.
It simplifies the whole system. If you try to teach an AI to learn contingency planning and steering control at the same time, the problem becomes impossibly complex. This way, CFO can focus the learning just on the social intelligence part.
And the whole system really hinges on that first component, the learned behavioral model, Kianda setter. This is the engine that holds all the social intelligence. What does this model have to learn during its training?
It has to do two critical things. First, it has to stochastically forecast multi-agent trajectories, so predict a whole range of plausible futures. Second, and this is the social intelligence part, it has to capture the codependencies between all the agents. It needs to know not just where the human might go, but how the robot's action causes that potential human movement.
And where does it get this knowledge?
It's all trained offline. It uses a massive data set of recorded multi-agent interactions, position, velocity, all of it, paired with those high-dimensional LiDAR scans.
And the source mentions something key about this data. The behaviors it learns from are goal-directed, but not necessarily optimal. Why is using imperfect data so powerful?
Well, if the model only learned from perfect expert driving, it would be really rigid. It wouldn't know what to do when a human does something a little weird, like driving too aggressively or being too cautious.
Right.
By including these suboptimal, some risky, some conservative drivers, the model learns the full distribution of plausible, real-world human behavior.
So it doesn't just learn the best way to drive. It learns the whole spectrum of how humans actually drive, flaws and all. That makes it robust.
Exactly. And this brings us back to the structure of the model, that conditional autoregressive normalizing flow. The autoregressive part is what's critical for modeling causality.
Let's break down autoregressive.
It just means that the probability of an agent's future position factorizes sequentially. So agent A's position at time tau depends on everyone's position and actions up to time t-1. It creates a chain of dependence.
So if the robot nudges forward at second 1, the model ensures that the human's predicted braking at second 2 is mathematically dependent on that nudge. It builds in cause and effect.
Yes. The model can't predict a response that happens before the action that caused it. It correctly models that dynamic back and forth, which is the whole essence of the co-leader model.
And tying this back to the normalizing flow part, that's the math that connects our easy-to-search policy knobs, the Z's, back to the physical states, the S.
Right. For the human agents, their Z's variables are just sampled, representing their uncertainty. But for our robot, its Z's variables are the free parameters we get to optimize.
So by choosing the best set of robot policy knobs, we're fixing the controllable parts of the decision tree, and then optimizing that choice against all the possible uncertain human futures.
Which brings us right to the mathematical heart of the system. The planning criterion, LCFO, equation 2 in the source. This is what defines a good policy.
Okay, so the goal is to find the policy parameters that are most likely to lead to success.
Yeah.
But because of the human uncertainty, you have to maximize the expected quality of the policy over all possible human behaviors.
Right. We can't guarantee a human will yield, but we can plan the policy that maximizes our chances of reaching the goal safely, weighted by the probability of how that human will react.
Let's do a slow dive into the three terms inside that objective that define the plan's quality. Term 1, the behavioral prior. What is that doing in plain English?
The behavioral prior is the realism check. It uses the whole learned behavioral model to score the likelihood of the planned joint behavior. It makes sure that the combined path of the robot and the human is plausible.
So if my plan requires the human to suddenly brake from 60 miles an hour or to swerve impossibly,
That plan gets a massive penalty. The term stops the robot from making up fictional plans that rely on impossible human cooperation. It grounds everything in the reality learned from the data.
this is the safeguard against that arrogant, overconfident planner we talked about.
Exactly. It enforces social realism.
Okay, term 2 is simpler. The destination likelihood.
That's the motivation engine. It just encourages the robot's planned path to end up near the goal. It provides the drive to get the task done.
And term 3, maybe the most critical for safety, the goal constraints.
This is the safety layer. These are your hard constraints, like collision avoidance. It's basically an indicator function. If the planned path is safe, this term is fine. If a near collision is predicted, it gets hit with a huge negative penalty.
So in practice, if the planner even explores a policy with a high chance of a near collision, that safety penalty just tanks the score no matter how fast the plane is.
That's the mechanism. It ensures CFO stays safe while it's negotiating. It tries to find the fastest, most effective route that is still statistically plausible and physically safe.
And now we can see mathematically why the other planners fail.
Right. If you look at the objective for the underconfident planner, its formula literally excludes the term that models the human's response. So the math forces it to find the most conservative, passive, weighting trajectory, because that has the highest guaranteed safety score against all uninfluenced futures.
The frozen robot is just the mathematically required outcome of an objective function that ignores influence.
Exactly. And then the overconfident planner, its objective assumes control over both agents. By maximizing the joint goal as if it controls the human, it ignores that behavioral prior, that realism check.
So it assumes the human will behave optimally, which to the robot means yielding right away. And if the human doesn't, it's already committed to a move that ends in a crash. The math just confirms the failure modes we see.
Precisely. Passivity comes from ignoring influence, and aggression comes from assuming total control. The co-leader model is the only way to get optimal performance in a real social system.
Theory is great, but the real test is performance. So the researchers tested CFO against its baselines using the CRLA driving simulator, which is a really high-fidelity environment for this kind of research.
And they focused on scenarios that specifically require cooperation. They forced the robot out of its comfort zone and into situations where it has to negotiate to be efficient.
Let's detail the three benchmark scenarios they used. First up, the left turn scenario.
As we've been discussing, the robot needs to turn left. The oncoming car has uncertain intent. This tests its ability to probe, to edge forward, and then execute that conditional decision. Turn if they yield, stop if they don't.
Second, the highway overtaking scenario.
Why?
A very common but tricky task.
It's difficult because the intent of the car in front of you is unknown. You need to change lanes to pass, but they might speed up to block you or they might slow down to let you in.
So the robot has to plan its move contingently.
Right. If they speed up, it needs a safe abort plan to tuck back in. If they slow down, it needs to seize that opportunity quickly.
And third, the right turn at a stop sign.
This is all about merging and yielding. The robot needs to turn right into a lane, but there's already a car in that lane. Does that car slow down and let you in, or maintain its speed? Again, you have to signal, wait for the response, and execute a conditional turn safely.
Now, when you're judging these planners, you need clear metrics. You can't just measure if they succeeded eventually. You have to measure the quality of that success. And the experiments use two critical metrics here.
The first one is the easy one. Goal reaching success rate, RG. This just asks, did the robot eventually get to the goal? Even if it took ages or had a close call, it's just a measure of completion.
But the second metric is the real differentiator, the one that separates a functional robot from a frozen one, the near expert success rate, RG.
RG star is the gold standard. It requires the vehicle to reach the goal as quickly as an expert human would, so efficiently and without any near collisions.
So if you're safe but slow, you fail. If you're fast but unsafe, you also fail.
You have to have both.
Okay, so let's dig into the results in Table 2, because they really show the severity of the failure modes. We'll start with a success story, the CFO method.
Across all three scenarios, CFO showed remarkable balance. It got near perfect RG, so it always completed the task. But critically, it also got near perfect RG star.
And that is the definitive proof. Active contingency planning lets the robot negotiate and complete these maneuvers quickly and efficiently. It achieves human-level performance.
It maximizes its opportunities without ever dropping that safety net.
Okay, now let's look at the other side of that coin. The failure of being too conservative. The underconfident planner.
The underconfident planner got a perfect RG in all scenarios, 30 out of 30. It always reached the goal, eventually.
But it's RG star.
Was a definitive 0 out of 30 across all scenarios, 0% success when it comes to efficiency. This is the quantitative proof of the frozen robot. In that left turn scenario, it will always stop and wait for the other car to pass, even if the human was trying to yield. It missed every single opportunity to negotiate. It's safe, but it's completely dysfunctional.
So we know where safety without efficiency gets you. Paralysis. Now for the other extreme, the overconfident planner.
The overconfident one also got a high RG, 30 out of 30. It always got to the goal, and usually pretty fast. But its RG star was terrible, like 9 out of 30 in the left turn, 12 out of 30 in overtaking.
So it was failing the no near collisions part of the test.
Constantly. This confirms that its aggressive planning, which just assumes the human will obey its master plan, leads to unsafe behavior 70 to 80% of the time the human does something unexpected.
So if the oncoming car doesn't yield, the overconfident robot is already committed to its turn.
And you get a near collision, or worse. It's a dangerous driver. CFO really stands alone as the only method that manages that critical balance.
The source also had a really useful comparison between CFO and model-free reinforcement learning like PPO. Why is that comparison so revealing?
So model-free RL, if you give it enough time, it can learn an optimal policy. The experiments show PPO eventually gets to 100% success rate. But the problem is how it learns. It needs extensive online training.
Which, in a simulator, means trial and error.
And the error in this world is a crash. Before it learns a good policy, the PPO agent has a significant number of collisions. It has to crash hundreds of simulated cars to learn the delicate balance of negotiation.
And that is the fundamental practical advantage of CFO.
Yes.
Because CFO learns its behavioral model entirely offline from observational data. It uses that model during planning to compute safety mathematically.
It figures out what's safe using those goal constraints and plausibility checks. It doesn't need to actually experience crashes during deployment to learn how to be safe, and that makes it a much more viable path for actually putting this technology on the road.
It's a huge paradigm shift. And it also gives you that crucial benefit of interpretability, right? Since CFO explicitly represents those forking future paths, you can look inside the robot's reasoning.
You can actually ask the robot, why did you choose to edge forward? And it can show you the math that favored that plan, along with the safe recovery path it had already calculated. It's not a black box.
So this deep dive has really confirmed the central evolution that's required for AI operating in the real world. These autonomous systems, they have to move beyond fixed trajectories and embrace these closed-loop conditional policies that are actively contingent on others.
Right. The world is a social environment, so AI has to become a social planner.
It has to.
And CFO successfully merges two things that were separate challenges before. First, that active contingency planning with the co-leader model. And second, grounding that plan in a fully learned data-driven behavioral model that understands the full, messy spectrum of human behavior.
It gives the AI the ability to both influence its environment and react to it responsibly. So if you're out there listening and you're not building a self-driving car, why should this shift matter to you? What's the broader relevance here?
Well, this is a foundational concept for any complex multi-agent system in an unpredictable environment. Think beyond cars.
Like what?
Imagine robotics on a shared factory floor coordinating with human workers. Or complex logistics systems with humans and automated handlers, even automated commerce agents negotiating prices with other AIs or with people.
Okay.
Any system where Agent A's efficiency depends on successfully negotiating with Agent B benefits from this. It's the move from a purely computational tool to a system that can manage the social contracts of interacting in the real world.
And if these systems are becoming social planners that actively probe and negotiate using subtle actions like edging forward to get a response, It raises a really fascinating and maybe provocative question for the future.
Mm.
If an AI agent is optimized for efficiency, and that optimization requires it to make moves designed to provoke a certain response from a human like edging forward to force a yield that's planned provocation. We regulate driving now based on physics and right-of-way. But if we introduce AI agents whose core function includes planned influence,
Yeah, where does that go?
will future traffic laws need to explicitly account for and maybe even regulate these strategies of planned provocation?
Yeah.
It just adds this whole new layer of social engineering into something as mundane as driving to the store.